So let's look at L'Hopital's rule itself, and I'm kind of building it up here, so I'll show you what it is, what it says. So L'Hopital's rule says, suppose that f of a equals g of a, and those are both equal to 0, and that the derivatives at a both exist, and that the derivative of g at a is not equal to 0. A lot of things here in the hypothesis of this theorem, and we'll talk about why those things have to be true. But if all of that is true, then the limit as x approaches a of f of x over g of x is equal to f prime of x over g prime of x. Now, this is a lot of notation here that might not mean anything to you in a second. I'm sorry, it might not mean anything to you now. I will explain it in a second. I'll give you a second to write it. Let's talk for a second about all of these conditions in the hypothesis. First of all, why would g prime of a have to not equal 0? Otherwise it would be undefined, so we would get an undefined answer, we would get 0 on the bottom. All right? Why would f prime of a and g prime of a have to exist? Yeah, they're both part of our answer. So since they're both part of our answer, if they don't exist, then our answer doesn't exist. So these things right here are kind of things that take care of themselves. If you try using L'Hopital's rule and one of these isn't true, then you're not going to get an answer that makes sense, and you're going to have to make an adjustment then. So they're kind of built into the formula. This part is not built into the formula. That's why I have it highlighted here in blue. This is really important because if this is not true, then it doesn't work. So what this is saying is f of a and g of a are both 0. So this is saying that if we go back to the sine of theta over theta example we looked at earlier, what we would end up with is 0 over 0. So what L'Hopital's rule is saying is if we have 0 over 0, then we can take the derivative of the top and the derivative of the bottom and plug our a value into that instead of this. And actually, I have a typo here. Those should be a's in there. So what L'Hopital's rule says is if we try taking the limit, we get 0 over 0. Take the derivative of the top, take the derivative of the bottom, put a in for that, and see what happens. Kind of cool, huh? Maybe. We'll see it in action. You can decide if it's cool or not after we do that. Here's a stronger form. I put it up here now, mostly so you can write it down. This is what happens if, in the last example, g prime of a is equal to 0. So if g prime of a equals 0, then we can do the same thing. So this says that g prime of a is not equal to 0 on the interval. I should say when a is not equal to x. But what this says, it's a slightly different format, but we can take the limit again. And essentially what this is saying is we could, if we get another indeterminate form, if we get 0 over 0 again after we take the derivative, we can take the derivative again. And if we had to, we could take the derivative again. And we can do it as many times as we need to until we get something that we know what the answer is going to be. And a lot of times it's going to go to infinity. A lot of times it's going to be 0. A lot of times it's going to be some other constant. And this is kind of an important thing down here. If it exists, if it doesn't exist, then you might have to do something else. Okay? So the stronger form of L'Hopital's rule looks the same as the original one, except we throw this limit in here also in front of the derivatives. And that just allows us to take the derivatives over and over again. So I want to take a second here and show you why this works, why we can take the derivative of the top divided by the derivative of the bottom, and it gives us the same as the limit of the functions themselves. And what I'm going to do is I'm just going to manipulate this a little bit. So this is going to equal the limit as x approaches a. And let me say this is not something you're going to have to be able to do. It's not something you're going to have to recreate, so you don't have to write it down. I just want to show you what's going on here. Remember that we said that f of a and g of a are both equal to 0. So I'm going to start this by rewriting this as f of x minus f of a. Did I change anything on top when I did that? It's Instead of f of x by itself, now I have f of x minus f of a. Did I change anything? I did not change the value of the numerator because we said f of a equals 0. And this is why this has to be true. This is why g of a and f of a have to equal 0. Because the proof of it requires us to be able to do this. So the numerator, we're going to write f of x minus f of a. The denominator, I'm going to write g of x minus g of a. Then what I'm going to do is I'm going to divide the top and the bottom by x minus a. And since I'm doing it to both, I'm really not changing the value of it again because I'm really just multiplying by 1 when I do that. So I have the limit as x approaches a of f of x minus f of a over x minus a, and all of that over g of x minus g of a all over x minus a. Now let me ask this. Does this part right here of the quotient look familiar? So the limit as x approaches a of f of x minus f of a over x minus a is the numeric derivative of f at the point A. You guys remember that formula? Kinda, sorta. So what we have on top is f prime of a. And what we have on the bottom is g prime of a. So by doing this manipulation, we can change this limit right here into this quotient right here that actually doesn't even involve a limit. Now, the stronger form of L'Hopital's rule requires a little bit more in the proof. This is a proof of the first one that I gave you. This is the form that we'll use most often. Usually you won't have to do the derivative more than once. If you run into a problem that you would, then the proof would be a little bit more involved, and we don't really need to spend the time on that right now.